In this video, we're going to use our understanding of gravitational fields to understand something new about electric fields. And so if this is the surface of the Earth, a place where I know that there is a uniform gravitational field, if I place an object in that gravitational field, I know that it's going to accelerate downwards. And so that gravitational field exerts a force mg on that mass and would cause it to move to the ground. And so everywhere in this space, no matter where I put that object, I know that there must be a uniform gravitational field because no matter where I put it, I'm getting the same gravitational acceleration. And so what we normally say is that when that object is on the ground, then it doesn't have any height. It doesn't have any gravitational potential energy. And so we say the gravitational potential energy at this lowest point, UG, would be equal to 0. But then, of course, we know if we were to raise that object up some distance, then we say it has some gravitational potential energy that is equal to mgh. In order to move that mass upwards, if I wanted to do that at a constant speed, I could apply a force that is equal to mg, and I could do that over a distance h. And so in general, we could just equate the change in energy of this object to the work that I've done on it. And so the way that we get that mgh is we say that the final energy, EF, minus the initial energy, EI, is equal to the force I exert times the distance over which I exert it. The initial energy, because of me defining the height equal to 0 on the ground, the initial energy is equal to 0. The final energy is gravitational potential energy. The force that I exerted in order to lift that object is equal to mg, and the distance over which that I exerted that force is h. And so we say that if I apply a force of mg over a distance h, that I've given that object some gravitational potential energy. We know that it has gravitational potential energy because if I were to let go of that object, that gravitational potential energy would get converted into kinetic energy and the object would move in the direction of the gravitational field. And so I would like to point out three things about this example that we've drawn here. First, the force that is exerted on this mass, whether it's the force exerted by the gravitational field or the force exerted by me in lifting it up, is mg. The energy that this mass has, the gravitational potential energy that it has, is equal to mgh. And those are two quantities that we're fairly used to, but in order to understand what I'm going to talk about with the electric field, I want to define a new quantity, which is called potential, just potential. And that is going to be equal to G times H. And the way that I want you to think about potential is, if I know G and H, then at all points in that gravitational field, the potential tells me if you place a certain mass at this point, you know how much gravitational potential energy it's going to have. And so independent of the mass, okay, I could tell you the mass later. If I know G and H, then I know the potential in that gravitational field at that point. In my picture up above, at a particular point, P, if I know the strength of that uniform gravitational field, and I know how high up the point P is above the surface, then for any mass m, I can tell you what the gravitational potential energy will be at that point. And so in that, from that perspective, the potential, the gravitational potential, is important because for any mass m, I can tell you what the energy will be. On Earth, we have a very real-life example of a gravitational field, but in order to get a uniform electric field, the example that I'm going to use is a couple of parallel plates. If I take two plates, and on the left plate, I cause it to have a positive charge. So everywhere on this plate, I have a positive charge. And then on a second plate, on the right, everywhere there is a negative charge, then everywhere between those two plates, there's going to be a uniform electric field. That electric field is going to point, as always, from the positive charge to the negative charge. And if you think back to our picture for the electric field between 2 point charges, it looks different than this. It's not a uniform electric field because the lines look a little bit different. But if you remember the line directly between the positive and negative charge, the electric field line pointed straight from the positive charge to the negative charge. And so in imagining the electric field between a positive and negatively charged plates, you can just imagine it as a bunch of pairs of positive and negative charges. Between them, there is an electric field that looks just like as I've drawn in the blue. And so that electric field points to the right. We know that if I place a positive charge Q in that electric field, that it will feel a force in the direction of the electric field because it has a positive charge. That force would be to the right. And so I want to think about those three quantities that I've defined down below for a gravitational field example. The force that object would feel is equal to the charge Q times the strength of the electric field E. If I wanted to move that charge in the direction opposite the electric field, then I've got to do work in order to do that. The charge wants to move to the right, but if I want it to move to the left, then I have to exert a force F. Just like in our gravitational field example, I have to exert a force of mg in order to lift it up. I have to oppose mg. In our example here, I have to oppose the electric force which acts on that particle QE. And so the force I'm exerting is F, and I can exert that force over a certain distance. And so let's say that I exert that force over a distance d. If I do that, then the energy that charge would have due to me doing work and moving it in the direction opposite the electric field would be the force I exert, which is Q times E, over that distance d. And so we haven't said this explicitly yet, but in doing this, I've given that charge some electric potential energy. So instead of gravitational potential energy in the gravitational field, this charge gets electric potential energy in the electric field. And similar to my example on the left, I want to define potential as the product of the electric field and its position in that electric field. We have another name that we use for the potential in an electric field, and that is voltage. And so this is also called voltage. And for voltage, we use the symbol V. And so in my picture for the gravitational field, I define somewhere as being the place where the gravitational potential energy or the gravitational potential is equal to 0 because I say that the height is equal to 0. And similarly in my picture, I want to call somewhere the place where the voltage or the potential or the electric potential energy is equal to 0. And so typically we will say that that is the place between two plates where the negative plate is. And then on the left-hand side, the voltage there will just be equal to V, or the maximum voltage that it is between those two plates. And everywhere between there, we have different voltages that are somewhere between 0 and the voltage on the positive plate. Similar to our gravitational field example, the voltage V tells me that if I place any charge Q at that point, what the electric potential energy would be. And so independent of the charge that I'm going to place in that electric field, what is the potential for that charge to have an electric potential energy? And so pulling this all together now, if I have the form of the equation for electric potential energy being QED, and that is equal to Q times V, the electric potential energy at any point is equal to the magnitude of the charge Q times the voltage at that point. But what we find with electric potential energy is the same thing as what we find with gravitational potential energy, and that is really only changes in either of those things matter. Because somewhere we have to define some arbitrary place where H is equal to 0 or V is equal to 0. And so for that reason, I'm going to write this equation as the change in electric potential energy is equal to Q times a change in voltage. And so the work required to move a charge Q across a potential difference delta V is equal to that change in energy. And so the work, W, is equal to Q times delta V. And this is because, pulling this all together, we know that any change in energy here, a change in electric potential energy, is equal to the work that was done on that charge. If we remember the units for these quantities that we've known previously, work is measured in joules, energy is also measured in joules, charge is measured in coulombs, and voltage we've seen could be measured in volts. But now you can also see that a volt is defined as energy per unit of charge, joules per coulomb. Let's say again that I have an electric field which points to the right. So everywhere this electric field is uniform. And in that electric field, I label 2 points, A and B. Those 2 points are separated by a distance d. If the voltage at any point in that electric field is equal to the electric field times the position in that field, and A and B are just 2 points along the same line in that electric field parallel to the electric field, then I could say that the voltage at A minus the voltage at B is equal to the electric field times the distance between those 2 points. Which is to say that if you wanted to know the potential or the voltage at any point, let's say A, then you would need to know the potential at point B, and then know the strength of the electric field and the distance between those 2 points. And a few important things that I would like to point out here from this example is that the voltage at point A is greater than the voltage at point B. And this is because electric potential decreases in the direction of the electric field lines. If I move in the direction of the electric field lines to the right, the voltage decreases. This is true for gravitational fields as well. If I move in the direction of the gravitational field, then the gravitational potential or the gravitational potential energy will decrease. I guess what we're saying is if I place a positive charge in that field anywhere, as it moves to the right, its voltage will be decreasing, and therefore its electric potential energy will be decreasing. To go along with that, I would like to say that when a positive charge moves from point B to point A, there has to be an external force that does that, because I'm raising the voltage and I'm raising the electric potential energy of that charge. And so an external force, like me taking the charge and moving it from point B to point A, is required for that to happen. And when the electric field applies a force on that charge and moves it itself from point A to point B, that is the electric field that's doing work. And so when a positive charge moves in the direction of the electric field is doing work on that charge, and when I move it in the opposite direction or something else moves it in that opposite direction, then some external agent is doing work on that charge. Now I want to look at the electric field and the potential around a point charge. And if we remember, if I have a positive charge, everywhere around that positive charge, there is going to be an electric field which points away. Because if I placed a positive test charge anywhere around this positive source charge, then it would feel a force directed away, and the electric field points in the direction that a positive charge would feel a force. So at this point P, I would like to know what is the potential at that point. Previously, we have said that the electric field is the force per unit charge that exists around a charge. And if the force is K times the magnitude of the source charge, the thing producing the electric field, times the magnitude of the test charge divided by the distance between them squared, and the test charge has a magnitude Q, then the electric field has a strength of K times Q over R squared. And in this video, we've defined potential as being the electric field times the position in that electric field. And so in my picture up above, if point P is a distance R away from the source charge, then the electric potential then is the electric field times R, or K times Q divided by R squared times R. And so therefore the electric potential at any point around a point charge, V, is equal to K times Q divided by R.